All right, you rascally chemistry kids. So next installment is start talking about rate and concentration, right? So the ultimate goal of what we're doing here is to learn about rate law, all right? And so what we do here is we look at the reactants in a reaction, and we identify kind of how changing the amount of those reactants, the concentration, affects how quickly that reaction occurs, right? So it's pretty calculation heavy, but essentially what this allows us to do is predict how fast a reaction goes when we change how much the concentration of a reactants, right? So we have to rely on some experimental evidence for that, but once we kind of calculate that value as a rate constant, we can then predict what happens in experiments we haven't run yet, okay? So that's where we're going with this. So those of you in my class, right, the question to which I will be referring is ChemQuest number 43, that last page, that skill practice page, number 1, A through F. Although if you're just watching this from afar somewhere, you can just do this as a practice, okay? So here's how we're going to begin this question, all right? And the number 1, A through F kind of lays out the order in which it's going, but these are kind of the order we have to go in to figure this out, okay? So the first thing we're gonna do, right, is identify the reactant order, right? So when we say the order of the reactant, what we're referring to is kind of a value. So for example, if I were to double my chlorine dioxide, what sort of impact would that have on the rate, okay? So if I double chlorine dioxide and my rate doubles, we'd say that's a first order reactant. If I double chlorine dioxide and the rate quadruples, that'd be a second order reactant. So that's what we mean when we say order, okay? So in 1A, I want to calculate what is the order with respect to chlorine dioxide. So we have two different reactants. So I'm actually gonna have to find out how chlorine dioxide affects the rate, and this singularly, and then how the iodine affects the rate singularly. And we gotta come up with little values for those that we'll plug in to a rate law equation in a little bit, okay? So, get warmed up. You got your calculator? Better have a calculator because I want you following along, trying to do these things as we go, okay? Calculator, ChemQuest, notebook, whatever you're writing in. All right, so 1A. All right, I want to calculate the order with respect to chlorine dioxide, right? So I want to know how changing my concentration of chlorine dioxide affects the rate over here, this number in this part of the table. So what I need to do, and this is not so tricky, we just got to be really careful, is we have to pick which two experiments to compare, all right? And the way to tell that is if I'm trying to identify how chlorine dioxide affects the rate, I need to pick two experiments where the iodide remains constant and the chlorine dioxide is what changes, all right? So it's an important rule in science, right? Whenever we're doing multiple experiments, we should really only change one thing at a time, right? Because that allows us to kind of dial in exactly how that one variable affects the outcome. So in this case, the variable I'm concerning myself with is the concentration of chlorine dioxide, right? And so I need to identify two experiments where the only thing changing is chlorine dioxide, right? So I'm going to look at these. Compare reaction 1 or experiment 1 to experiment 2. You should notice that my chlorine dioxide changes, right? This goes up about by a factor of 3, right? My iodide ion stays constant, so that automatically tells me, oh, I can use experiments 1 and 2 to compare for chlorine dioxide. Okay, so what I'm going to do, and here's my formula I'm going to use, right? I'm going to go high concentration over low concentration. The nth power is going to be equal to the high concentration rate over low concentration rate. Okay? And so what I have is my high and low concentration and the corresponding rates. Those are the numbers given to me on the table. What I'm going to solve for is that n. And once I know that value for n, I then know So like if N comes out equal to 1, I know that chlorine dioxide is a first order reactant. If N comes out to 2, I know it's a second order reactant, and so on. So really what I'm doing is I'm solving for N in this equation right here. Okay? So now I'm just going to plug values in, all right? And just do some math, basic algebra, all right? So my high concentration, now I want to know it with respect to chlorine dioxide. So my high concentration and my low concentration are those two values, right? So for my order with respect to ClO2, it's going to be 0.90 over 0.30, right? So this is my high concentration and my low. To the nth power is going to be equal to the corresponding high, so this is 9.045 times 10 to the negative third molarity per second over 3.350 times 10 to the negative fourth molarity per second. Okay? And so I get my handy calculator out. I plug these numbers in, I chug away, right? And I should end up with a value that looks like this. 3 to the nth power equals 27. All right? So those of you who are fairly mathy, right, you can automatically pick out what the value for n. 3 raised to what power equals 27. Okay? Not super difficult, but if you're not so mathy, you just can't do math in your head like that, right? How do we solve for an unknown exponent in algebra, right? You should have been taught that in your algebra class at some point, but I'll just show you, right? So if I want to know the value of an unknown exponent, right, and that's my variable, I'm going to do this, right? So I'm just going to take this equation over here, this bump over here where I have a little bit of space. Okay, so 3 to the n equals 27. All right, so I'm going to use a log function on my calculator, right? And all I'm going to do is replace it. So I'm going to go n is equal to the log of 27 over log of 3. All right, and so what I do there, that logarithm function, that's a way to solve for exponents, right? It's a, I don't know, you have to actually math teach you all the little tricks of what a log actually does. I just know this will solve for my unknown exponent. So when I do that, I should get n equals 3. All right, now, so what? So what if n equals 3? What does that mean? That tells me, so the n, remember, tells me that chlorine dioxide is a third order reactant in this reaction. Okay, so what does that mean? That means, okay, now listen carefully. Because this is a third order reactant, that means if I were to double my chlorine dioxide, for example, right, my reaction rate should go up 2 to the third, or factor of 8. Okay, so doubling this means my reaction rate goes up by a factor of 8. Okay, so that's what a third order reactant. If it was a second order reactant, right, doubling this would raise the rate 2 to the second power, or this would go up 4 times. Does that make sense? So when we say that the reactant order with respect to chlorine dioxide is 3, that means if this doubles, this is going to go up 8 times. That's what that means. Okay? Now, so we're going to remember, I'm going to write n equals 3 above this guy, n being the order of that reactant, right? And that's going to be important when we get to our rate law question later. Okay? So I'm going to leave my handy equation up here and erase the rest, right? Because I'm only partway done. So I found my answer to A. A is the third order reactant. B, right? We have 2 reactants, right? So we're not only going to change this, but now we want to identify, well, what about iodide, right? What if I change the concentration of iodide? Is that going to have the same impact, or a lesser impact, or a greater impact, or what? Or any impact at all? Okay, so what do? Go to B, right? we need to look at iodine on the table, right? So we're going to go through the iodine values, and again, we need to pick 2 experiments to compare, okay? Where the only thing that changes is the iodine value this time, okay? So we've already identified that experiments 1 and 2 work for chlorine dioxide, which means they will not work for iodine, right? So let's look at the iodine. So we notice between experiments 1 and 2 we're the same. Between experiments 2 and 3, right? Now we have a change in our iodine, but if I compare experiment 2 to 3, I'm also changing my chlorine dioxide between those two, all right? So I can't compare 1 to 2, I can't compare 2 to 3. My only other option is whether 1 and 3 work. So do I have the data here to actually finish this problem, right? So if I compare experiment 1 and 3, right, my iodide does change, my chlorine dioxide stays the same. Ding, there we go, we got one that works, right? So we're going to use experiments 1 and 3. Now, if I had a longer table with a bunch of values, you might find that more, you can compare, there's multiple options. In this case, there's only one option for each one where we can actually do the comparison, okay? So I'm gonna compare experiment 1 to experiment 3, and I'm gonna plug my numbers in. So my high concentration is 0.80, right? A low concentration is 0.40, right? To the nth power is going to be equal to 5.360 times 10 to the negative 3 molarity per second over 3.350 times 10 to the negative 4 molarity per second. Okay? And when I do the math, I should get 2 to the nth power equals 16. That means I'm going to have a pretty big order there. 2 to what power is equal to 16? All right? So again, you mathy people, you could probably figure that out. That's a 4, right? But how do I solve this? I'm just going to go n equals log of 16 over log of 2, right? So n will be equal to, phone call, be right back. Okay, so now, right, we know that n equals 4 for our iodine. Okay? Now, so one thing that we also have to look for is, now that we have two reactants, and we know the order with respect to both of those reactants, is what's our overall order for this reaction, right? And that's pretty simple. So overall order is just the individual orders added together, right? So I'm going to go 3 plus 4 equals 7, right? So doubling the concentration, right, of both reactants would bring our order up to 7, right? So it'll be 2 to the 7th power faster, right? So that's actually really big orders. Not too many reactants out there that are actually like that, okay? Anyway, so now we've identified how the two reactants singularly impact the rate. So the reason that's helpful, right? The reason what this does for us is it allows us then to make predictions, right? That's a lot of what we do in science. We get some information so we can make predictions about new situations, right? That's the power of science, is its predictive power, right? So next step then, right? Letter D says, write the rate law for this reaction, okay? So I know that n equals 3 and n equals 4. Let's write a new formula up here for rate law. All right? So rate law looks like this. The rate of the reaction is equal to K. Now, K is the letter we give for our rate constant. That's going to be a number that will be the same for all reactions, including chlorine dioxide and iodine, at least in this situation, right? So we're going to take that K value, that rate constant, times the molarity of CO2. Right, actually, hold on. Let me just give you the base formula. I'm going to put reactant 1 to the nth power times the molarity of reactant 2 its nth power, right? So what we do then is we're going to now plug in the values that we know. So for this, we can actually pick any reaction off the table. Doesn't matter which one, just as long as we use all of our values from that particular experiment. All right. So let's just pick. Let's see. Actually, it doesn't really matter. Let's just pick one. But for this particular reaction, my rate law would look like this. Rate is equal to K times the molarity of ClO2 to the third power times the molarity of I minus to the fourth. So that would be the rate law for this particular reaction. And so if I want to know what my rate constant is, okay, okay, I'm going to solve for K, and I'm going to plug in values from one of these reactions. And I'll just pick reaction 1, since it's the top one, okay? So, in this case, my rate, I already know, is 3.350 times 10 to the negative 4 is going to be equal to K, right? And K is what I'm solving for. So, for this rate, my concentration of ClO2, okay, times 0.30 to the third times 0.40 to the fourth. Right, is how I'd write that, okay? And what I should get, so I'm going to go this to the third times this to the fourth, so I should get 3.350 times 10 to the negative fourth is equal to K times 6.912 times 10 to the negative fourth, okay? And then, of course, divide both sides by that, and I should get K is equal to 0.484, right? Now, we're going to notice that our value for K actually has some funky units, all right? And really, the units are there just to make sure all the units work out. But it basically comes out to 0.44 times 1. We'll get to those in a second. We'll do that for a future tutorial. All right. But what this does, this value right here, right? It's not units. We'll get to units in a later tutorial. But what it does is I can now take this value, plug it in to my rate law, right? And I can solve for the rate based on any concentration I want to make, right? So now that I know my rate constant, I can predict the rate at various concentrations for which I don't actually have data for. That's essentially what we do there, okay? Okay, so that's rate constant. So again, what is rate law allowing us to do? First of all, it allows, we pick out how our individual reactants singularly affect the rate, right? The way we do that is we find out the order of that reactant, right? So we use that high concentration over low to the nth power is equal to the high over low rate, right? So we solve for n in that case, each reactant separately. Then we plug that into our rate law equation, plug our numbers in, we solve for our rate constant. Once we know that rate constant, we can then make predictions about how fast that reaction will go when we have various concentrations of our two reactants. And away we go. All right? Keep to it.